Imagine the universe as a grand stage where everything is in constant motion, from the tiniest particles to the largest galaxies. For centuries, we believed time and space were fixed, seconds and meters the same for everyone, everywhere, as if the universe followed a single unchanging script. But then, a young Albert Einstein rewrote the rules. In 1905, he introduced special relativity, revealing that space and time are woven together into a single dynamic fabric, space-time. This idea shattered old beliefs and opened the door to a universe far stranger than anyone had imagined. This fabric isn't rigid. It can stretch and squeeze, warping in response to motion and energy. The speed of light is always the same, no matter how fast you move or where you are in the cosmos. That's the universe's ultimate speed limit, a cosmic rule that nothing can break. To keep light speed constant, space and time themselves must flex and adapt, bending to preserve this law. It's a cosmic dance. Your experience of time and distance depends on how fast you move, and even the order of events can shift depending on your perspective. Special relativity isn't just a theory. It's a new way of seeing the cosmos, where the stage itself bends and warps with the actors, forever changing our understanding of reality. One of the most astonishing consequences of Einstein's special relativity is called time dilation. This means that moving clocks actually run slow, not because of any mechanical malfunction, but because of the very nature of time itself, which bends and stretches depending on how fast you're moving through space. The faster you travel through space, the slower you experience the passage of time. This isn't just a theory. It's a fundamental part of how our universe works. Scientists have tested this idea using incredibly precise atomic clocks, placing one on the ground and sending another on a high-speed jet. After the flight, the clock that traveled on the jet was found to be slightly behind its twin on the ground, just as Einstein predicted decades earlier. Time, it turns out, flows at different rates for different observers, depending on their speed and motion relative to each other. Even the GPS satellites orbiting high above Earth must account for time dilation, or else our navigation systems would quickly become inaccurate, sending us kilometers off course. Time dilation isn't just science fiction. It's a real, measurable phenomenon that shapes our technology and our understanding of the universe every single day. To grasp the strangeness of time dilation, let's consider the famous twin paradox. Imagine identical twins, Stella and Tara. Tara stays on Earth, living her life as usual. Stella boards a spaceship and travels near the speed of light. For Stella, time slows down. Her clocks, her heartbeat, her aging. Meanwhile, decades pass for Tara on Earth. When Stella returns, she's aged only 10 years. Tara, however, is now much older. The twins, once identical, are now separated by a striking age gap. This isn't a contradiction, but a real consequence of our universe's laws. A high-speed journey through the cosmos is also a journey into the future. Not only does time warp at high speeds, space does too. When we approach the cosmic speed limit, the very fabric of the universe behaves in ways that defy our everyday experience. Special relativity tells us that objects moving near light speed appear shorter in the direction of motion. This strange phenomenon is known as length contraction, and it's a fundamental part of how the universe works at extreme velocities. It's not an illusion or a trick of the eye. To a stationary observer, a fast-moving object is genuinely measured to be shorter than when it's at rest. The faster it moves, the more it contracts, shrinking further as its speed increases. Imagine a spaceship 100 meters long at rest. At 90% the speed of light, an outside observer measures it at just 44 meters, a dramatic difference caused by its incredible speed. Only its length shrinks. Height and width stay the same, so the ship looks squashed only in the direction it's moving. Both astronaut and observer are correct in their own frames. Space, like time, is relative. What you measure depends on how you move. As we move, space and time warp to uphold one law. The speed of light is absolute, unchanging for everyone, everywhere in the universe.